Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you, and hope all of you are fine. Very happy new year to all of you, considering that I am recording this after 2019 started. So, hope everything is fine at your respective end. Now, as you know, this is the DADM 2 course, Data Analysis and Decision Making 2, and we are going to start the third week lecture, and this whole course is for total number of hours is 30. That means, each week we have 5 classes or lectures, each lecture being for half an hour. So, in totality we have 60 lectures, and we are going to we have completed 10, and we are going to start the 11th lecture. And my name is R.N. Sengupta from the IME department, IIT Kanpur. Now, if you remember, we were discussing my utility functions, then the concept of safety first principle, the concept that how different bounds, the Chebyshev bound, Markov bounds could be utilized, and based on that how problems could be formulated as a simple optimization problem, where you want to have a look at different concepts of these are not the direct use of utility functions, but they are a way how could you can use optimization, and when you are using optimization, obviously the concept of utility function would be utilized time and again. So, in today's lecture we will discuss something to do with not a different concept, a similar concept depending on how we can utilize it, as loss functions. And why loss functions are important, I will come to that, and we will try to utilize that in this. I will give you examples and then try to utilize it later on, how loss functions could be utilized. And remember that these loss functions would be important when you are trying to analyze different decision making, where non-parametric decisions are important. So, let us consider what we mean by loss functions. So, in course of any statistical study, any type of estimation, any type of forecasting, any type of prediction, we have some set of observations. Now, this set of observations are taken from the pool, that means you have the population. Population, I mean the whole set of observations which are applicable, from which you can take the data, and you take a certain observations. Now, for any statistical study, by the way, we did discuss few of these things in DADM 1, but I will again repeat it. It will be needed, that is why. Why it will be needed, I will come to that later. So, please have the patience and please bear with me. Now, for any statistical observations or studies or estimation, prediction, forecasting, we, as I said, that we pick up set of observations, those are a small n in number, and our main aim is basically to utilize those set of observations to draw some meaningful conclusions. So, as it says, in the course of meaningful conclusion about the population, because you have a small sample and the sample characteristics should be such which you are going to study, because based on the data you want to predict or forecast something about the population characteristics. It can be the mean, median, standard deviation, the value of the ratio of the mean to median, what is skewness, kurtosis, whatever it is. So, in course of statistical estimation problem, observations collectively known as the sample pertaining to a data set are regarded as realization of the random variable. So, each observation, when you pick up, they are realized value of the random variable, and with which is associated a probability law or a distribution. So, we will basically mention it as P, but basically it is small f of x or capital F of x, depending on how you are trying to explain that. Small f of x would basically be for the PMF for the PDF, and capital F of x would be the CDF function, which is the cumulative distribution function. Usually P is specified by the cumulative distribution function, as I just mentioned, namely f of x, and it is basically the summation of all the properties from the minimum value of x to that value, particular value of x, based on which we are trying to find out the cumulative distribution function. Generally, f is not completely known, and because there are parameters in the distribution. So, there can be the shape, scale and location parameter, which we denote by, for the PDF, for the PMF, shape, scale and location, alpha, beta, gamma. And these alpha, beta, gammas are for the population. When you pick up a sample, we may not know that, we want to estimate. This is the general task. So, generally f is not completely known, and we are usually interested in drawing statistical conclusion about the parameters, where theta, which is basically a function of the distribution function. So, our main aim is this. Now, in a parametric model, the assumed functional form of f may involve some unknown algebraic constants, which are interpreted as the parameters, as I said. Example, in the normal distribution, you have the mean, which we generally denote by the mean mu and standard deviation sigma. J are generally the parameters, mu and sigma. Then similarly, say for example, you have in the exponential distribution a and theta, in the Poisson distribution theta, in the binomial distribution n and p. So, there are different parameters for each distribution, which are, as I said, again I am mentioning, from the population are unknown. So, when you pick up a set of observation which is mentioned here, so you pick up an observation and they realize, well, they are random variables, which is x1 to xn. So, actually when you pick them up, you have, and they are realized, they become small x1 to small xn. So, they are known to you. These are the sample observations, random variables to choose a suitable, and based on these random variables x1 to xn, we choose the statistic. Statistic is basically the characteristics which you are getting from the sample, which is T n, suffix n, which basically means the number of observations. So, it is a functional form of x1 to xn. So, T n is basically function of x1 to xn. So, it can be, if you are trying to find out the mean, it can be the weighted mean, simple mean, exponential mean, whatever it is. So, as that T n estimate, so what we are interested is basically to find out that how does the T n which we have found out basically gives us some information about the theta, which is the parameter which we are working on, which you want to find out from the population. Now, whenever you are picking up a set of observations and when you have found out T n, our main concern is that the T n should be as close as possible to theta. So, if you remember, we have discussed two important properties when we were doing DADM 1. So, one was basically unbiasedness, that means the expected value of T n in the long run should be equal to theta, and one was consistency, in the sense that as the sample size n increases, the probability of the difference between the T n value and theta, that means the bound, slowly tends to 0 as n tends to infinity. So, if I write it down, technically the first would be, I will write the first one, erase it and then write the second one, considering the space is limited here in this slide. So, the first one will be the expected value, which is unbiasedness, which you have already considered. There are proofs for that, but I am not going to go into that. So, let us erase it. So, then we have the consistency, which means limit n is the sample size is to infinity, probability of T n minus theta, okay, being less than or equal to, yes, I should basically specify it, less than or equal to some epsilon. Epsilon is a very small value, tends to 1, that means the difference always becomes as low as possible. So, it basically is the variance in the long run would be decreasing. So, if these properties are met, obviously we are happy with this parameter or this estimate T n. Now, the issue is two things, whether it is actually possible to find out T n. So, answer is that in many of the cases T n may not be, we may not be able to find out T n even if we consider these two properties, or even if we ignore these two properties, the functional form of Tn may not be possible to at least delineate or give an expression. So, coming to this imposing consistency which I mentioned, and unbiasedness does not always lead to a unique estimate of theta. So, some may be consistent, some may be unbiased, and all these combinations. A very good idea would be to locate an optimal estimator within the class of this consistent and possible unbiased estimator, which will do our work or which will give our result. So, consistency would be more important, and if they are unbiased, then obviously well and good. So, we will basically concentrate on consistency. One idea would be to choose a non-negative metric. So, we want to basically measure it, and that measure what we do is known as the loss function, which is defined for all values of theta and all values of Tn, which we find out, where Tn varies over the sample space and it is a subspace of the real number n depending on the number of parameters which are there. So, what we are interested to find out is basically find out Tn, which is a functional form x1 to xn, which is the realized value, such that the functional form of a loss means some type of negative gain we are going to have in choosing Tn, such that there is a difference between Tn and theta in their actual value, that will give us some loss, some negative value. So, you want to basically have a functional form of that loss and try to basically understand that how that loss can basically be optimized or reduced. Obviously, we will try to reduce it, because if Tn is closer to theta, well and good, it is actually what we want. If Tn is definitely far away from theta, that is actually we do not want. So, few of the loss functions which you may have seen in DADM1, but I will again mention it. So, one is basically the quadratic loss function or the square error loss function. So, in this case you see that if I basically find out and draw or delineate or mark delta is basically this. So, which is basically the difference between theta hat and theta. Theta hat is basically Tn, which is the estimate of theta we are going to find out from the sample. So, the difference of theta hat and theta is basically delineated along the x axis, and the loss function is basically delineated or drawn along the y axis. So, in this case it is a quadratic loss function. So, hence the loss function which we will draw along the y axis would be theta hat minus theta whole square. So, all the values which are positive would be drawn on the right hand side, which considering theta hat is greater than theta, and all the values which are negative will be drawn on the left hand side onto the origin, which is theta hat minus theta is negative. But obviously, as the loss function is quadratic, so if theta hat minus theta is plus 2 and theta hat minus theta is minus 2, the square value becomes 4. So, both on the right hand side and the left hand side of the graph, that is in the first quadrant and the second quadrant, the height of that function f of x, which is basically L of delta, is basically of equal quantum. Now, the advantage of this loss function is that if you try to minimize this loss function, it gives us some information of trying to basically minimize the variance. Because what is variance? Variance is expected value of theta minus theta hat, and try to find out the expected value of that, which is basically the dispersion which you are talking about, the variance. And if you minimize that, obviously it will lead to the fact that minimizing the loss function considering quadratic loss function also leads to the minimum variance. Another, which is good, and obviously there are good results for that, theoretically is very nice. But obviously practically it would not be nice, as I will try to give you some examples later on within few minutes. So, another loss function which could be utilized would basically the mod loss function. So, which is linear loss function in the sense that both positive and negative loss functions are of equal weight. So, hence and the difference of theta hat minus theta, if it is positive, it is given a positive value, not a square value on the first quadrant, and if theta hat minus theta hat is negative, then also it is given a mod value, which is of the same quantum on the second quadrant. So, obviously it will be a 45 degrees line both in the first quadrant and the second quadrant, but in the first quadrant it is positive and the second quadrant it is negative, but we are trying to delineate is accordingly. Now, consider this, the loss functions which I just discussed was the mod loss functions, which is linear loss functions. Now, consider the positive part is weighted. by a factor which can be more than 1 or less than 1. So, in that case, in this example which we see in front of us, which is in the slide, the value of which you are giving to the weight, which is when it is on the positive quadrant, which is the first quadrant, considering theta minus theta hat is positive, is more than the weight which you are going to give it to in the when it is in the second quadrant. That means, for any positive deviation we are going to give a linear weightages, obviously linear functional form would be there, but the weightages would be much more. While if it is in the negative direction in the second quadrant, we will give a weightages which will be less than the first quadrant, which means that if the difference is, say for example, plus 2 and in another case the difference is minus 2, we will multiply plus 2 by a unit which is, say for example, 1.5, but in the case when we are getting a minus 2, we will only multiply it with 1 or less than 1, which means that we are penalizing. The penalization of the loss for positive one is higher, and similarly for the loss for the negative one is lower. Then obviously you will think that why not switch it, that means we give higher weightages for the losses which are in the second quadrant and give lower losses, comparatively lower losses which are for the losses which are in the first quadrant. So, obviously it will happen that in that case the loss would look like this, when the weightages given to theta minus theta hat minus theta which is positive, which is the blue one, the weightages which you are giving for that is less, then and that is what we are drawing in the first quadrant is less than the value of the weightages which you are giving in for theta minus theta which is negative, which is there being drawn in the second quadrant. So, obviously we are trying to unequally penalize the losses for the positive and the negative losses, but they are linear in nature. Now, technically this linear part has an issue, because if you see the line at the origin, so obviously there the concepts of continuity and differentiability are an issue. I am not going to go into the details about that. So, Hall-Varian in the 1960s gave a very nice loss function which is known as the linear exponential loss function, and that was mainly in the concept of trying to find out in the economics perspective. So, this asymmetric or linear non-linear loss function was basically known as Linex loss. So, the part Linex, L-I-N-E-X, the first part Li basically means the Lin basically means the linear part, and Ex basically means the exponential part. So, if you see the slide, the loss function is linear exponential in Linex loss function. This p should not be there red, so it should be small. So, Linex loss function is a part, if you check this loss function, forget for the time being the parameter b, only concentrate in the equation form which is given inside the square bracket. So, here basically exponential a into theta minus theta hat, that is the first term which is exponential part for the Linex loss, and the second part which is linear is given as minus a into theta minus theta hat minus theta, and there is a minus 1. Now, why this loss function is useful? Let us go slowly. If you consider the the loss function for the part, and as the shown in the graph, if a is positive, remember that means the parameter is positive, then as theta minus theta hat increases, which is in the first quadrant, the weightages on the overall loss which is coming out from the exponential part slowly starts dominating the linear part. Hence, the part in the first quadrant is much more penalized than in the case when it is in the second quadrant. That means, when a is positive and you are basically trying to find out theta minus theta hat which is negative. That means, overestimation is more penalized than the underestimation in the case for the Linex loss when a is positive. Now, let us consider the picture when a is negative and still you basically want to delineate or draw the Linex loss function considering a is negative, and both for the first quadrant and the second quadrant. Now, here the loss looks like this, in the sense when a is negative and you are trying to basically take theta hat minus theta. So, in that case the exponential part will dominate the linear part on the second quadrant, and when again in the same case when theta hat minus theta is positive and a is negative, then in that case linear part which will dominate the exponential part, because that negative part would bring that ratio down as fast as possible. So, in this case you will have the exponential dominating in the second quadrant for theta hat minus theta being negative and theta hat plus minus theta being positive, the linear part will dominate, which means that again we have a case where it is an asymmetric loss function, but underestimation would be more dominated than the overestimation. Now, consider this loss function, that why it is important. Let us basically consider that theta hat minus theta is very small, this is in and around the value of origin, which is 0. So, if you basically expand the exponential form, so the first term would be 1, the second term would basically be plus a into theta hat minus theta divided by factorial 1. The second term is basically again is it will be plus a square into theta hat minus theta whole square by factorial 2, and the terms will continue. So, if you consider the first term 1 and minus 1, they will cancel out as given here. I am not writing it out, please listen to me carefully, you will understand. So, basically if you expand, again I am repeating, if you expand the exponential part, the first term is 1. So, 1 and minus 1, which is already there in the Linux loss function, cancels out. The second term part for the expanding of the exponential part would be a into theta hat minus theta in the numerator divided by 1 factorial in the denominator. So, again that cancels out with the second term which is given in the Linux loss function. The third part in the expansion of exponential part is plus a square into theta hat minus theta whole square, which is in the numerator divided by factorial 2, and it will continue. Now, consider theta hat minus theta is a very small number. So, obviously square is a smaller number and cube and other powers basically are quite smaller number. Say for example, theta minus theta hat is 10 to the power minus 2, then theta hat minus theta whole square becomes 10 to the power minus 4, theta minus theta hat cube becomes 10 to the power minus 6, and so on and so forth. So, if you ignore the cubic term, the fourth part term, the fifth part term for the expansion, and obviously 1 has already cancelled, plus a theta into theta minus theta hat and minus a into theta minus theta hat are already cancelled. So, you are only left with the third term, which is the quadratic term. So, you will see for very small values of the difference between theta minus theta hat, their Linux loss function almost exactly belongs to is almost the quadratic loss function, which means a special property of the Linux loss is that it basically penalizes both overestimation, it can also penalize all underestimation depending on how you have basically framed the problem. And in the special cases when theta minus theta is almost closer to 0, the Linux loss basically can be replaced by the quadratic loss function, and all the properties of the quadratic loss functions can be utilized. Now, we will basically discuss 3 simple examples in order to basically make you understand that how these values of a being positive, being negative, and theta minus theta hat, whether overestimation important or underestimation important, or whether we depending on the problem you will take the situation where overestimation is more important or underestimation is more important. So, consider a company is going to launch a new product, and the company is launching a new product in a sense that there are other competitors also. I will read the statement which is given in the slide, but let me first explain it. So, here the company is launching a product considering that is a refrigerator or a TV or a fridge or an AC, whatever it is. Consider for the time being the product which you are launching or you are launching the market, that warranty life is say for example given as 6 months. Now, there are competitors and 6 months you have estimated for yourself from the marketing study. Now, consider 2 scenarios. Scenario 1, the competitors have a similar type of product, but their actual warranty life is less, which is basically 4 months. So, in this case what happens? 6 months you basically give a product. So, in that case when the product is basically floated in the market, people will be more tempted to buy your product because you are giving a warranty of 6 months. So, obviously the initial sales for your product is much higher. But remember the actual product which is already there in the market, similar type of product which is being floated by, which has been floated by your competitor, that 4 month is the actual warranty life which should have been, but somehow either due to your erroneous calculations or due to your marketing strategy you gave a a warranty life of 6 months. Now, initially the product was sold quite well, but generally the products would be start failing in and around 4th month. So, obviously, and you have already given a warranty life of 6 months. So, obviously, you have to pay some penalty to the customers and basically repair their products from the money from your own pocket, which means the initial positive thing has basically been now been wiped out by the negative thing, which means that this overestimation and underestimation has to be analyzed in such a way that the market which you captured in the initial stages, whether it is lost due to the loss of sales as it happens later on during after the 4th month, when you basically find out that people are basically not being satisfied as the product has started failing in and around the 4th month, in spite of the fact that you have basically given a warranty life of 6 months, which was wrongly calculated. So, obviously, you have to understand which is more, the initial sales was better, or whether it was basically better to give you the warranty life of 6 months. Now, consider the other way, you actually the warranty life is 8 months and you have given a warranty life of 6 months. So, now remember one thing, 6 minus 4 and 6 minus 8, these both things are plus and minus, minus 2 and plus 2. So, if you basically consider from the point of view of the quarterly loss function, it will be 4 in both the cases. Now, let me come back to this example. So, it is basically 8 months and you have given it 6 months. So, initially the products sold by you would be much less, because people will be more attracted for the warranty life which is 8 months, but as they find out their products which you have brought from the your competitors start failing. So, obviously, people will be more attracted to your products later on, because they find out the warranty life is actually what it should be, which is 6 months, and slowly you gain your market. So, initially you had a loss, in the sense the market share was less. Now, you will slowly gain the market share. So, and the first example scenario 1 is that initially you gained a big market share, but slowly you started losing the market share and the confidence of the customers, because many of the products which you sold in the market had to be repaired, because the warranty life which you stated as 6 months is not actually 6 months, is basically 4 months. So, in this case, overestimation or underestimation is more penalized or less penalized. You have to basically analyze this problem and basically state the condition based on which you will basically frame this problem. So, now with this, let me read the problem. Consider a company plans to launch a new product, say a refrigerator in the consumer market. Also, suppose that similar products from different manufacturing already exist in the market. Then the company is expected to give some warranty for the particular product, that is the refrigerator, to its customers in order to sell the product. Now, if the value of this warranty is more than the average time of the failure for the product, then the aforesaid mentioned company needs to replace the damaged product it sells or face litigation charges. Obviously, if you give a warranty life which is less than what it actually should be, or more than actually, obviously in one of the cases there would be some litigations. On the other hand, if the warranty period is less than the average failure time of a particular product, similar product in the market, then the company loses the market share to its rivals, as naturally customers are willing to buy the refrigerator from the competitors who assure a higher warranty period, as I mentioned. Under such a situation, it is definitely advisable to estimate the warranty lifetime using an asymmetric loss function. Whether you want to penalize or less penalize or more penalize will depend on the situation what you are facing. What values of A, that is the parameter which I said, A being more positive, that is, and theta hat minus theta would basically be penalized more, and in the case when A is negative, then theta minus theta hat which is negative will be penalized more, because exponential part will dominate in the first quadrant in the first case when A is positive, and exponential part will dominate in the second quadrant for the case when A is negative. So, what values of A one should use would then depend on the level of importance our company places on the overestimation versus underestimation, that is the cost of the litigation versus the cost of a loss in the market share of the company has to be analyzed. So, with this obviously there would be more other examples coming up for overestimation or underestimation specifically, but with this I will end this 11th class and continue the discussion later on for the from the 12th class, and try to basically give you an example where the loss function could be utilized, and later on see how we will try to basically merge it with the utility function and asymmetric loss, and try to solve many of the non-parametric problems which are there to be discussed for this course. Have a nice day and thank you very much.